Hi, I'm Desmond Edagisi, and I welcome you to mathematics class. Today we'll be looking at the topic, Introductory Calculus. And under our topic for today, we'll learn about the differentiation of algebraic functions. Remember, there are all kinds of functions. We have logarithmic functions, trigonometric functions, and so on. But for this level of our class, we'll be focusing on the differentiation of algebraic functions. Let's go on. During the course of our class today, these are the things we expect to learn. First, we'll learn about what calculus is all about. Next, we will also learn what differentiation is. Following that, we will learn about how to differentiate from first principles. Next, we'll learn the standard derivatives of some basic functions. And finally, we'll learn about the rules that govern differentiation. Let's go on into our class. Now, calculus. What exactly is calculus? Calculus, in a nutshell, is the mathematical study of change. Whenever we have a quantity that changes its value regularly, that is, it does not have a constant value, but its value changes over time, we make use of calculus to study and to model such behaviors. Let's take some typical examples. For example, the temperature of a particular area that varies or changes over time, or the velocity of a falling object at a particular time, or even the variation in stock market prices at a particular time. All of such quantities that vary over a period of time can be studied using calculus. Now, the word calculus has a Latin origin, and it means small stone. The word small stone is used because it's like understanding something by looking at the little pieces of that thing. So we have two main branches of calculus. We have differential calculus, which is also called differentiation. And that is what we'll be studying today. Differential calculus or differentiation cuts something into small bits and pieces in order to find out how much it changes over time. It is concerned with rates of change and the slopes of curves. The other branch of calculus is the integral calculus. It's also called integration. Integral calculus joins or integrates, and that's where the word comes from. Integrates the little pieces together to find out how much exactly there is. It is concerned with the accumulation of quantities and the areas under and between curves. Let's go on. Now, differential calculus and integral calculus, they are essentially inverses one of another. That is, they are opposites of each other. As we go on in our class, we'll learn that if you have an original function and you differentiate it, that is, it goes through the process of differentiation, what you have is a derivative. So we move from original function to get a derivative. Now, if we integrate our derivative, it will give us back our original function. So that's why we say differentiation and integration are inverse processes, one of another. But remember, we'll be focusing on differentiation in this class. In our next class, we'll learn exactly what integration is. Let's go on. Now, differential calculus is the process of finding the instantaneous change of various functions. The product of the process of a differentiation is what we call the derivative. So the derivative of a given function is also called derived function, is the result of a mathematical differentiation. These are terms that we need to be familiar with. As we go into our class, we'll make use of these terms: derivatives, differentiation, and the likes. Let's go on. Now, in determining the changes that certain quantities undergo, we can easily depict this using graphical slopes for better illustration. Take, for instance, a car that is moving at a constant rate of acceleration or a constant rate of velocity. We would have a linear graph that is straight because it has a constant rate of change. Now, to find the rate of change for such a quantity would not be a problem because you would have constant rates of change along every point along your graph, the straight line graph. But the problem comes when it is a non-linear function. Now, for cases of non-linear functions where we have curved graphs, for instance, a graph like this, we cannot directly find points to find our slope because at each point along our curve, a change is taking place. That is, there is no constant value. Our values are changing constantly. Therefore, to measure change for such quantities, what we do is to find the rate of change at a point. Let's say P at a point P. Now, to find the rate of change here, using slope formula, which of course is rise over run, which is our slope. Rise being the values along our y-axis, and of course our run being values along the x-axis. At this point, there is no value for our y-axis. It's basically 0. Along the x-axis also, it's basically 0. So we have a slope that is impractical, 0. Differentiation helps us solve such cases that are difficult to handle. If we zoomed into our point P here, if we zoom long enough, imagine we're using an instrument. At a point, it appears straight, a bit straight, where we can now pick our points. Differentiation helps us to pick points and then shrink them back to 0, so we do not defeat our initial purpose. Let's take this example here. A function y given as f of x. Let's assume this has been zoomed into. So we're going to take our point at P here, which we were asked to find, and another point Q. At the end of the day, we'll shrink, that is, we'll bring our Q so close to our P that we'll have a value either 0 or very, very close to our 0. Now, if we take our new point here and trace down to our x-axis, we would have a change between our initial x and our new point as delta x. The sign delta in Greek means change. So it's a change in x. The change in x between our first point and our second point here is denoted with a dx. Same way, if we trace our point Q, we'd also have our function here as x plus our delta x. This function here, as we're using for an example, can be any function y is equal to x squared, y is equal to x cubed. Just for example's sake, let's use this function. The coordinate values of our points P are x and f of x, while the coordinate values of our points Q are x plus the x, which is this point here, x and the change that we have, delta x. And our other value along the y-axis is f of x plus delta x. Again, like we said earlier, our delta x is the symbol we use for increment or small change. So our change here, between here and here, that is the new point Q, which we picked arbitrarily, is actually very small. And at the end of the day, mathematically, we'll see that differentiation helps us shrink this Q back to our P. So at the end of the day, we find what we're looking for, that is the rate of change at our point P. Now, the gradient of our graph, y is equals to f of x, is the rate of change of y with respect to x at the point P. And that is what we seek. To get our slope, we'll find our difference in y, which we call the rise, over our difference in x, which we call the run. The difference in y is denoted with a delta y, that is change in y. The difference also in x is denoted with a delta x, which also means change in x. So our delta y from our graph is f of x plus delta x minus our initial point on the y-axis, which is f of x, all over also our new point on the x-axis, which is x plus delta x minus x. So all of this gives us our slope. If we took out our like terms, we would have f of x plus delta x minus f of x minus x here cancel out to give us 0, and we are left with delta x. So this is our slope, f of x plus delta x minus f of x all over delta x. That is our slope. Now let's go on. The gradient of PQ, that is our gradient here, will be a better approximation if we take Q closer to P. Hence, like we said earlier, we will shrink our value. This Q was chosen arbitrarily in our course to find the slope. What if we bring it closer here, or here, or here, or here? So if we have our Q here instead, we've succeeded in shrinking this value here, which is our incremental change, would also reduce. If our Q were here, that means our incremental change would be our change in x, much, much smaller, so small that it could be insignificant. So, as our PQ, our gradient, it becomes better when Q gets closer to P. As our change in x, delta x becomes smaller, we get an increasingly accurate measure of the gradient of our curve at x. But since we cannot let delta x, from the formula that we saw earlier, we cannot let delta x be completely 0. If we mathematically impute this as 0 immediately, we'll have an inconclusive answer. So what do? We do the next best thing. We make our delta x tend to 0. That is, it gets closer to 0. It keeps reducing. That is, it's shrinking until it gets very, very close to 0. And the symbol that we use to denote that is our delta x tending to 0. This means delta x tends to 0. That is, it keeps shrinking until it gets to 0. It is expressed mathematically as this. We say our delta y all over our delta x, that is our slope, with the limit of delta x tending to 0. Hence, the formula for differentiation from first principle is this. We say dy dx is equal to the differentiation of y with respect to x. That is, remember we said we're looking for our points P here. The rate of change that is present in the point P, the rate of change of y with respect to x at this point P, which is dy dx, is what? Our delta y all over delta x with delta x tending to 0. And we have our slope, remember, as f of x plus delta x minus f of x all over delta x with delta x tending to 0. This is the fundamental formula of the first principle of differentiation. Now, understanding certain notations that we make use of in differentiation. Dy dx signifies the derivative, that is the product of differentiation of y with respect to x. So wherever you see a d dx, for instance, like this, it means that this is our differentiating operator. And whatever comes after it is the function. So if you have a d dt of 4t cubed minus 5, it simply means that you are differentiating the function 4t cubed minus 5 with respect to t. So d dx is also the differentiation of a function with respect to x. In this case, our function here is y. That's why we have y there. So we have dy dx, which spells out as the derivative of y with respect to x. Another point to quickly take note of, in the course of differentiation, there may be another notation that you come across. If you have a function f of x, for instance, to denote that you are looking for the derivative of this, we simply use a prime. So we have f prime our function x. This means that the derivative of this original function, this is our original function, and this is its derivative. So our prime here is a sign or a symbol that we also use to denote a derivative, along with our differentiating operator here. Let's go on. Now that we've derived the formula for differentiation from first principles, let's take a practical example and try to work it out. If we're asked to differentiate the function f of x is equal to x from first principles, how do we go about that? Quickly, this is what the graph of our function looks like. F of x is equal to x. We see that this is a linear graph, so it should be easy to find using differentiation from first principles. We have a point Q, and we have another point P. Our delta y tells us that we have a change between this point and this point. Our delta x also tells us that we have a change. This was our original x, and this was our x plus that change. Also, this was our original function f of x, while this is f of x plus delta x, Hence, we have our original formula derived as the differentiation from first principle formula. We said our delta y over delta x is f of x plus delta x minus f of x, that is, f of x plus delta x minus f of x, our point here, all over our x plus delta x minus x. Of course, x minus x is 0, and we have our delta x left. Hence, we have our delta x there. All we need to do is to impute our function x into the formula to get what we seek. Let's quickly do that. So we have x plus delta x imputed minus our f of x is substituted for x, and of course we have our delta x. X here would cancel out our minus x, leaving us with delta x as our numerator, while we also have delta x as our denominator. If we cancel this out, we'd have 1. At this point, we impute our limit. Remember, we said we have a limit as delta x tends to 0. So we are shrinking our value here, delta x, by bringing p forward. If we keep shrinking this until it gets close to 0, we'd have at this point no delta x is present in our equation, so it does not factor out. Our 1 remains even if this limit is applied. It therefore means that the derivative, dy dx, if y is our function x, the derivative of x with respect to x is 1. The derivative of our y is equal to x with respect to s is 1. This is a fundamental knowledge that we need to keep at the back of our minds. As we go further into differentiation, we'll find that we'll make use of this knowledge all the time. Let's go on. Once again, let's take another example. Let's see how we can differentiate from first principle the function f of x is equal to x squared. Remember our first example was x, but now we have x squared. So how do we go about differentiating this function from first principle? So once again, remember our formula. We said delta y by delta x, or delta y all over delta x, is the function of x plus delta x minus the function of x all over delta x. This again is our fundamental formula of differentiation from first principles. The graph of our function here, f of x is equals to x squared, as we can see is drawn here, is a curve. Different from the graph of what we did earlier, where we had a straight line graph. In this case, it's a curve. And we have our point Q here and our point P here. So we have our value x here, while we have at this point x plus delta x. At this point, we have f of x. And at this point on our y-axis, we have f of x plus delta x. So from our formula, we know exactly what we are looking for, our slope, which is the f of x plus dx minus f of x all over x plus dx, minus x, which of course will give us dx. And hence we have our formula. So all we need to do at this point is to impute our given function, which is x squared, into our formula. So if we do that substitution, we have x plus delta x squared minus x squared, all replacing our variables here, all over dx. Now when we expand this and collect the like terms, we have x squared plus 2x delta x plus delta x squared minus x squared all over delta x. Of course, our s squared minus x squared will cancel out, and we will have left 2x delta x plus delta x squared, which we have here, all over dx. Now we have like terms in both our numerator and denominator, and that's the x. So the x comes out, and we have 2x plus delta x, all over dx. Of course, this cancels out again to give us 2x plus delta x. Now, at this point, we impute our limit as delta x tends to 0. So our delta x here is written out in full as the limit as delta x tends to 0 of, all in bracket, 2x plus delta x. Our delta x here, we said, is tending to 0. And if we do that, we'll be left with 2x alone. So our dy dx, which is our derivative, that is dx of y of course is our function, which is x squared, is equal to 2x. Therefore, the derivative of y is equal to x squared with respect to x is 2x. This again brings us to another fundamental knowledge that we need to understand as we go into the study of differentiation. We'll see what that rule is, but know that the derivative of x squared would always give us 2x. And if we have also the derivative of x cubed, it will also give us 3x squared. But as we go on in our class, we will learn about how that rule applies. Finally, let's look at another example. If we are asked to differentiate the function f of x is equal to 1 over x, this is what our graph looks like. Again, our point here will be x, and our point here will be x plus delta x. That is our change in x. Here we would have our point f of x, and here on our y-axis we have a point x plus delta x. And of course, that brings us to our fundamental formula of differentiation from first principles. So we have our slope, f of x plus delta x minus f of x all over dx as our formulas. All we need to do again is to take our variable from the given function, which is what? 1 over x, and impute into this formula. So we substitute wherever we find x with 1 over x. So we have 1 over x plus delta x substituted minus the substitute here again, 1 over x, all over delta x. This, of course, if we work this out and we group the like terms, we have x minus bracket x plus delta x all over x bracket x plus delta x. And this again, all over delta x. If we worked all of this out, we simply have minus delta x all over x in bracket x plus delta x and delta x out. This, of course, crosses out and leaves us with this. Minus 1 all over bracket x plus delta x bracket closed x outside our bracket. Now we impute the limit as dx tends to 0 into this our equation here. And we write it out in this way. It means that our dx here, as it tends to 0, we will be left with what? Minus 1 all over x and x. The product of x and x, of course, will give us x squared. So we have minus 1 all over x squared. And that is our final answer. The derivative of y, which is our function here, 1 over x, is minus 1 all over x squared. So once again, this is something we also need to put at the back of our minds as a fundamental knowledge as we go into further study of differentiation. Here are some standard derivatives. Of course, we've managed to solve some for ourselves, but in general, here are some standard derivatives and how to go about them. So whenever you have a constant k, for instance, the derivative of our constant is 0. So no matter what the constant is, if it's 2, 5, 10, 20, 100, the derivative of that constant is what? 0. Whenever also we have x, the derivative of x gives us 1. We solve that for ourselves from the fundamental principle of differentiation. Also, if you have x raised to a certain power, the derivative of that variable will give us the power multiplied by x raised to that power again minus 1. Also, the derivative of 1 over x would give us minus 1 all over x squared. The derivative of root x would give us 1 over 2 root x. The derivative of a constant multiplied by x, our variable, would give us the constant alone. And the derivative of our constant multiplied by our variable x raised to a power would give us that power multiplied by the variable multiplied by x raised to power n, which is our power, minus 1. So these are just some standard derivatives. Even as we go further in study, we'll find that we can just take the knowledge of these standard derivatives and impute them as the need arises in the course of calculation. Let's go on to learn about the rules that govern differentiation. Now, there are certain rules that govern differentiation as a process. The very first rule, and one of the most fundamental rules, is the power rule. The power rule. The rule states that the derivative of a power of x is equal to the product of the exponent times x with the exponent reduced by 1. It simply means that, for instance, if we have x raised to a power n, the derivative of this, that is our d dx, is this power coming down to multiply our x, still raised to our power, but in this case, we subtract 1 from it. So this is a fundamental rule. We'll take some examples so that we get the basic understanding. Now we have x cubed, and we've been asked to find the derivative function of x cubed. If we apply our law that we just learned, the power rule, we would what? Have our 3 here, which is our initial power, come down to multiply x, still raised to our power 3, but in this case we'll subtract 1. And of course this would give us 3x raised to power 2. And that's how simple it is. Let's take another example so that we'll get a better understanding. Again, we've been asked to find the derivative function for 2x raised to power 4. Again, if we apply our rule here, we'd have 2x raised to power 4. Derivative would be, again, we already have 2 as a constant. Our 4, which is our power here, again, comes down, which is 4, to multiply x, still raised to the power 4, but in this instance, subtracting 1. So what do we have? We have 2 times 4 times x raised to the power 4 minus 1. 2 times 4, of course, is what? 8. We have our x. 4 minus 1 is what? 3. So our answer, that is the derivative of 2x raised to the power 4, is what? 8x raised to the power 3. Very simple. Let's go on to learn about another rule. Now, when we have sum and differences in differentiation, there is a particular step that we must take. The rule of the sum and difference law states that the derivative of the sum or difference of 2 or more functions is equal to the sum or difference of their individual derivatives. And this is what our formula looks like. So the derivative of, for instance, f of x plus or minus g of x, which is another function, is equal to the derivative of f of x separately. So we'll find the derivative of each function separately, plus or minus the derivative of g of x, and then we add them or subtract them as the need arises. To put it in a simpler form, if you have y as your given function that has u plus or minus v, then the dy dx, that is the derivative of our y, is what? Du dx, that is the individual derivative of u, plus or minus the individual derivative also of v. So we simply add or subtract them as the need arises. Let's take some examples for better understanding. If we were asked, for instance, to find the derivative function for x squared minus x plus 5. So from what we've learned from the sum and difference rule, we'll find the individual derivative of x squared, find the individual derivative of x, and also find the individual derivative of 5. And then we'll minus or add them up as the need arises. So once again, let u be our x squared here. Let v represent our x here. And let w represent our 5. So the derivative of u, that is, u is x squared. The derivative of x squared from the power rule we learned would be what? 2 coming down. And of course, 2 minus 1, which is the remaining power, is what? 1. Whatever is raised to 1 is the same thing. So du dx simply is what? 2x. Next, our v is equal to x. Even from the first principles, we also learned that the derivative of x would always give us 1. So dv dx, which is the derivative of v with respect to x, is what? 1. Next is our w. We have 5. 5 is a constant. And we learned earlier that the derivative of any constant would give us 0. No matter the number, 2, 5, 10, 100, 1000, it would always give us what? 0. So now we have all our derivatives. We have 2x, we have 1, and we have 0. Subtraction and addition, the way it came from our question. So dy dx will simply be 2x, of course, minus 1 plus 0. And hence, 0, of course, goes off to give us 2x minus 1. So the derivative of x squared minus x plus 5 is simply 2x minus 1. If you follow the rules, you'll find that finding the sum and difference of any derivative is always very easy. Now let's take another example. If we were asked to find the derivative function for minus 2x squared plus 3x plus 1. Again, we'll simply let u represent 2x squared here. Let v represent 3x. And let w represent 1. Of course, you can use any letter. It's just for your own clarity. Next, we need to find the individual derivative of 2x squared, 3x, and 1. And at the end of the day, we simply add them up or subtract them as the need arises. So now that we know what to do, let's go ahead and do it. To find the derivative of u, which is 2x squared, following the power rule that we learned earlier, we'll simply have 2 come down to multiply our 2 and our x to give us 4x. The power that we have left on our variable x would be 2 minus 1. Of course, 2 minus 1 is 1. So simply, we still have x. That means that the derivative of u will simply give us what? 4x. Next, let's find the derivative of 3x. The derivative of a constant multiplied by a variable from what we learned looking at the integral table that we presented earlier is simply our constant left alone without the variable. So the derivative of v here, which is dv dx, will simply give us 3. Also, finding the derivative of w, which is 1. 1 is a constant, and we said the derivative of any constant, of course, will give us 0. So we simply have dw dx as 0. What we have to do next is to add up all our individual derivatives or subtract them as the need may arise. Let's do that quickly. So we have dy dx of our function here to be minus 4x. Remember, we have minus here. And that's our minus 4x plus 3 plus 0. And of course, 0 goes off, leaving us with minus 4x plus 3. Of course, we can rewrite this to make it a little bit more neater and would have 3 minus 4x as the derivative of our given function. Let's go on to learn about other rules. Another rule that we'll come across in the study of differentiation is the product rule. The rule states that the derivative of the product of two functions is equal to the first function times the derivative of the second function plus the second function times the derivative of the first function. Let's not get confused. Let's quickly look at it mathematically to have a better understanding. So if we are asked to find the derivative of the product of two functions, the function f of x and the function g of x are two different functions. If we were asked to find their derivative, we would do that by first multiplying our first function f of x by the derivative of the second function, which is g of x. So we have that on one side. Then we add it to the second function g of x times the derivative of our first function f of x. Of course, that's on the other part of our equation. So we have two parts to our equation. So for easier understanding, if y is our given function in question. And y is a product of two functions, function u and function v. Then dy dx, that is the derivative of y with respect to x, is what? U multiplied by the derivative of v plus v multiplied by the derivative of u. To understand this better, we need to look at some examples. Now, let's take this example. We've been asked to find the derivative function for 10x raised to power 6. So we have two functions here. 10 is a function, and x raised to power 6 is also another function. So what do we need to do? First, we need to separate our functions, now that we know what they are. And let's represent them. For instance, let u represent 10, and let v represent x raised to power 6. So the differentiation or the derivative of u, which is du dx, would be 0. Since our constant is 10, the derivative of any constant from what we've learned earlier is what? 0. V, on the other hand, is x raised to power 6. And dv dx, which is the differentiation or the derivative of v with respect to x, is 6x raised to power 5. Of course, I think we should remember by now our power rule. If we bring 6 down, we have 6 as a power left, minus 1, and that will give us 5. So we have 6x raised to power 5. So now we have all our factors in place. Let's follow our rule. The rule states that the differentiation of the product of two functions is what? U multiplied by dv dx plus v multiplied by du dx. We know what u is. Our u here is 10. We know what dv dx is. Our dv dx is 6x raised to power 5. We know what v is. Our v is x raised to power 6. And we know what du dx is. Our du dx is 0. So all we need to do is impute our values into our formula, and then we have our answer. Let's quickly do that. So dy dx, which is the derivative of our given function here, with respect to x is what? 10 times 6x raised to power 5 plus x raised to power 6 times 0. Of course, 0 times x raised to power 6 would give us 0. So all of this would give us 0. And we'll be left with 10 times 6x raised to power 5. 10 times 6, of course, will give us 60. And hence we have 60x raised to power 5 as our derivative. So that's the product rule. But let's take a look at another example so that we understand better. Now we've been asked to find the derivative function for two functions. One of that function is x squared plus 1, and the other function is x cubed plus 5x. So again, let u represent this first function here, and let v represent our other function here. Now du dx, that is the derivative of our function u here with respect to x, would give us, let's take a look at our function, x squared plus 1. If we used our sum and difference rule, we would have 2x plus 0. Following our product rule, the derivative of x squared would be what? 2 brought down, and the remaining power 2 minus 1, of course, will give us 1. And that's, of course, x. So we have 2x. The derivative of 1, which is a constant, is 0, which is, of course, out. So we have du dx as 2x. dv dx, meanwhile, v is our second function, x cubed plus 5x. The derivative of x cubed, of course, will give us 3x squared, following our power rule, while the derivative of 5x will give us 5, from what we learned earlier. So our dv dx is 3x squared plus 5. Now remember our formula again. dy dx is u multiplied by dv dx plus v multiplied by du dx. We know what our u is. Our u is x squared plus 1. We know what our dv dx is. Our dv dx is 3x squared plus 5. We know what our v is. Our v is x squared plus 5x. And we know what our du dx is. Our du dx is 2x. Now that we have everything we need in place, all we need to do is to impute our values into our formula to get our answer. dy dx, therefore, would give us u, which is x squared plus 1, u, dv dx, which is 3x squared plus 5, plus v, which is x cubed plus 5x, so this is v, times our du dx. Du dx, of course, is 2x. So if we simplified our equation here, if we worked all of this out, we would have 5x raised to the power 4 plus 18x squared plus 5. And that is our derivative. So now we understand exactly how the product rule works. Let's go on. Another rule, also important, that we come across in differentiation is the quotient rule. Quotient, of course, we know what quotient means. It has to do with division. So when we have two functions, one dividing the other, there are certain rules that we must follow. And it states that the derivative of the quotient of two functions is equal to the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the square of the denominator. To make it simpler, let's look at it mathematically. So if you have the derivative, the d dx, of two functions, one dividing the other, f of x being divided by g of x, we would have that as g of x multiplied by the derivative of f of x minus f of x multiplied by the derivative of g of x. All of that divided by g of x squared. In simpler terms, if y is u over v, dy dx, that is our derivative of y, with respect to x, would give us v multiplied by du dx minus u multiplied by dv dx, all over v squared. To understand this better, let's take a look at some examples. Now we've been asked to find the derivative function for 3x minus 4 divided by 2x plus 1. Now, let y represent our given function there. Okay? U is our numerator and v is our denominator. U is 3x minus 4 and v is what? 2x plus 1. Now, differentiating u, that is the derivative of u, which is 3x minus 4, would give us what? 3. Of course, if we use our sum or difference rule, the derivative of 3x would be 3. The derivative of 4 is 0. Hence, we have 3 as the derivative of u. The derivative of v, v being 2x plus 1, would be also 2. From our sum and difference rule, if we did that separately, the derivative of 2x would give us 2, while that of 1 would give us 0. So we simply have 2. So we have all that we need to plug into our formula. We have u, we have v, we have du dx, and we have dv dx. Now let's take a look at our formula. Remember our formula for quotients in differentiation. dy dx is v multiplied by du dx minus u multiplied by dv dx all over v squared. Let's plug in our values at this point. So we have v, which is what? 2x plus 1. This is v. We have du dx, which is 3. Minus u, which is what? 3x minus 4. So this is our u. Multiplied by dv dx, which is what? 2. All over v squared. Our v, of course, is 2x plus 1. So this is our v squared. So we have all our values plugged into the formula. Now, what we need to do next is to simplify our equation. If we do this carefully, we would have 6x plus 3 minus 6x plus 8 all over 2x plus 1 squared. Of course, 6x minus 6x, they cancel out. And we are left with 3 plus 8 all over 2x plus 1 squared. 3 plus 8, of course, will give us 11. And we have 2x plus 1 squared as our denominator. So our final derivative at the end of the day is what? 11 all over 2x plus 1 squared. And that's our final answer. Let's also take a look at another example. Using the quotient rule, find the derivative function for x squared plus 6 all over 2x minus 7. So again, let y be our given function. Once again, we say let our numerator be represented by the letter u, while our denominator be represented by the letter v. Du dx would give us 2x. That is, if we found the derivative of u, which is our function, that is x squared plus 6, would have 2x. While dv dx, that is the derivative of v, which is 2x minus 7, would give us 2. So again, we have all the values that we need to plug into our equation. We have u, which is x plus 6. We have v, which is 2x minus 7. We have du dx, which is 2x, and dv dx, which is 2. Let's take a look again at our formula for quotients. We have dy dx is v multiplied by du dx minus u multiplied by dv dx all over v squared. Let's impute our values at this point. So we have v, which is 2x minus 7, multiplied by du dx. Du dx is 2x minus u, which is x squared plus 6, multiplied by dv dx, which is 2. All over v squared. V, of course, is 2x minus 7, so our v squared is 2x minus 7 all squared. Now we have an equation. All we need to do is to simplify it again. If we multiply this out, 2x and 2x will give us 4x squared. 2x and minus 7 will give us minus 14x. Minus 2 multiplied by x squared would give us 2x squared. 2 also multiplied by 6 would give us 12. All over 2x minus 7 squared. If we work this out, we would have 2, which is common to our equation, at least our numerator, out. We have x squared minus 7x minus 6, all over 2x minus 7, all squared. And this is the simplest form that we can break this down into without going into too much details. This, again, is our derivative for our question, x squared plus 6 all over 2x minus 7. So once again, that's how the quotient rule works. The next rule we'll be looking at is the chain rule. The chain rule. Now, there are certain functions that will come across in differentiation that we refer to as the function of a function. That is, it's a function within a function. When we have such cases, the method that we use in solving such a case is what is referred to as the chain rule. As we go further, we'll take some examples, so we'll see exactly what the function of a function we're talking about is. But basically, the rule states that if f is a function of g, and g in itself is another function of x, then the derivative of f with respect to x is equal to the derivative of f of g with respect to g times the derivative of gx with respect to x. Mathematically, this is what it looks like. So if we have the function of a function, g of x is a function, but of itself is also another function of f. So this is an example of a function of a function. If we were asked to find the derivative of this kind of function, that is the dx of f of g of x, that would give us the differentiation of, that is the derivative of f of g with respect to g multiplied by the derivative of g of x with respect to x. In simpler terms, if y is a function of an inner function, we let u be the inner function itself, then y would be the function of u. This is to simplify such cases so that we don't get confused. And in solving this, we would have our dy dx, which is easier for us to understand, being dy du times du dx. Let's take a typical example for clarity. If you've been asked to find the derivative of, take this function for instance, 2x minus 5 raised to the power 10. If you look at it closely, you'll notice that 2x minus 5 is a function of itself. Now, all of the function in brackets, let's take that as another function, is also raised to a power 10. So it's like a function within a function. For such cases, we make use of the chain rule. And to do this, to simplify this, we simply say let y be our given function. The inner function here is what? 2x minus 5. Let u be that inner function. So u is what? 2x minus 5. And y therefore would be what? If y is 2x minus 5 raised to the power 10, and we've been told that 2x minus 5 is u, it therefore means that our y is what? U raised to the power 10. So this has helped us to simplify it while we go further to work it out. So we have u as the inner function and y as u raised to the power 10. Now du dx, that is the derivative of u here, if we worked on this, we would have 2 as the derivative of 2x minus 5. The derivative of 5 is a constant, of course, is 0. The derivative of 2x, of course, gives us 2. So we have du dx as 2, and dy du. In this instance, remember, we are working with respect to u. So dy du is what? 10, using the power rule, 10 will multiply u, and our power here will be 10 minus 1, and that will be 9. So dy du is 10u raised to the power 9. If we take a look at our formula here, we said our dy dx is what? Dy du times du dx. We have all that we need to impute our values into this formula. Let's quickly take a look. Dy du, we have our dy du, and that is what? 10u raised to the power 9. We also have our du dx. Our du dx is 2. So what we need to do is to impute our values, which is dy du times du dx. And that is 10u raised to the power 9 multiplied by 2. This, of course, is our dy du. And this, of course, is our du dx. So if we multiply this out, we would have 20u raised to power 9. Now it's simple, but we do not give our answers in this manner. Remember at the beginning, we said u would be used to represent 2x minus 5. So once again, we'll impute the original value of our u back into this equation. And that would give us 20 2x minus 5 all raised to power 9. We can leave our answer in this way, or we can multiply it out. But however we do it, our derivative is 20 multiplied by all bracket 2x raised to power 5 all raised to power 9. Let's take a look at another example. If we were asked to find the derivative function for the square root of 5x minus 3. So once again, we notice that this function is a function within a function. And hence, the formula or the method that we use to solve this can only be the chain rule. We have an inner function, which is 5x minus 3. Let's take the brackets, all the variables within our bracket as a function. That variable also is affected by our square root. And hence, we have what seems to be like a function within a function. Now, to help us simplify this, like we learned earlier, we'll say, let u represent our inner function, which is 5x minus 3. If 5x minus 3 is u, it therefore means that our y here is what? The square root of u. And the square root of u, from what we learned in indices, is also u raised to a power half. Now we have our u. To differentiate u, which is 5x minus 3, we would have 5. So the derivative of u with respect to x within our variables here is what? 5. dy du, on the other hand, if y is u raised to our power half, it therefore means that the derivative of y with respect to u would be u raised to power minus half all over 2. To work this out, all we need to do is remember our power rule. Our half would come down to multiply u, and hence we have 1 over 2 u. Half minus 1 would give us minus half. And that's why we have u raised to power minus half all over 2. Again, from our laws of indices, we could also express our u raised to power minus half as 1 over 2 square root of u. Now, if we apply our chain rule, let's remember our formula. The derivative of y with respect to x, which is dy dx, would be dy du, which we have as 1 over 2 root u, times du dx. Our du dx, of course, is 5. So all we need to do is to impute our values that we've gotten so far into our formula. I will simply have 1 over 2 root u, which is dy du, multiplied by du dx, which in this case is 5. If we multiply this out, we have 5 all over 2 root u. Five all over 2 root u. But remember, from the beginning, we substituted our 5x minus 3, which was our inner function, to be u. So we therefore need also to resubstitute our original value for u into our answer. And that would give us 5 all over 2 root 5x minus 3. This is our derivative of our original function. Now, in summary, we've learned all about calculus. We said calculus is a mathematical study of change. We also said there are two major branches of calculus. We have differential calculus and we have integral calculus. We learned that differential calculus is concerned with the rate of change and the slopes of curves. We learned that differential calculus also helps us to find the rate of change of one quantity compared to another. We also learned about the first principle formula for differentiation. We worked out the formula together. And I guess we won't forget that formula quickly. And whenever we have need to apply this formula, of course, we'll remember how to apply it. We said the derivative of a function y, that is dy dx, is our incremental change in y all over incremental change in x, with our incremental change tending to 0. We said that incremental change we know as delta x. So we say delta y by delta x, with limits as delta x tends to 0, is f of x plus delta x minus f of x all over delta x, with our delta x tending to 0. This is the formula that we derived for the first principle of differentiation. It's a fundamental formula that we must never forget. Next, we learned about the different rules of differentiation. We learned about a very fundamental rule, which is the power rule. We said that the derivative of a variable x that is raised to a power n would give us our power n multiplied by a variable x raised to our power, but in this instance, minus 1. We also learned about the sum and difference rule. We said if we have a number of functions added or subtracted one from another, we'll simply find the individual derivative of each function and add or subtract them as the need arises. So dy dx, which is the derivative of our function y with respect to x, is du, if u is one of the functions and v is another function, du dx plus or minus dv dx. Next, we learned about the product rule. We said when we have more than one function, that is two or more functions multiplied together, we use the product rule. And the product rule simply states that if y is our given function that has two functions, u and v, dy dx, that is the differentiation or the derivative of y with respect to x, would be u, which is our first function, multiplied by the derivative of our second function, that is dv dx, plus v, which is our second function, multiplied by the derivative of our first function, which is du dx. Next, we looked at our quotient rule. We said the quotient rule applies when you have two functions, one dividing the other. If y is our given function that has two functions, u, for instance, divided by v, we said dy dx would give us v multiplied by the derivative of our numerator function, du dx, minus u multiplied by the denominator function, in this instance v, which is dv dx, all over v squared. And finally, we learned about the chain rule. We said the chain rule is applied for functions that appear as functions within a function. We said if we have such an instance, for example, y being f of g of x, we let u be our gx, that is u be the inner function. Then we let u, of course, be the outside function or the external function. Dy dx in this instance, that is the derivative of our y with respect to x, would be the derivative of our external function, which is dy du, multiplied by the derivative of our internal function du dx. And that is what we've learned today. Now we're going to take one or two questions to see if we remember all that we've learned today. So quickly, if we're asked to differentiate 2x plus 1 raised to power 7, if we took a quick glance at this, what kind of function do we have here? If we know the kind of function we have, then we know what rule to apply. We have a function that is within a function. Remember, we just learned about the chain rule. The chain rule is used to solve situations like this. And see which of our options here is our correct answer. Let's solve this quickly. So once again, following our chain rule, we've said let u represent the inner function. Our inner function here is what? 2x plus 1. And let y represent our external function. So we'll have u raised to the power 7. Now we said dy, the x, that is, the derivative of our y with respect to x would be du dx times dy du. Or dy du times du dx. However you arrange it, it's all the same. So now let's find the derivative of our u here. Du dx. Using our sum and difference rule, if we quickly run through this, we would have what? Our derivative as 2. Because the derivative of 1, which is a constant, of course, gives us 0. The derivative of 2x would give us 2. Also, let's find the derivative of y with respect to u. And this would give us, using our power rule, this would give us 7u raised to the power 6. So we have the two factors that we need to plug into our formula to give us our answer. This, of course, is our formula. So let's go. dy dx would be what? Du dx, which is, du dx is 2, times dy du is what? 7u raised to the power 6. And of course, this is what? 14u raised to the power 6. So we'll quickly plug in our original value of u back into our answer to get our correct answer. And that would be 14 times u is what? 2x plus 1 all raised to the power 6. And that is 14 all in bracket 2x plus 1 all raised to the power 6. Of course, B is our correct option. And that's our answer. Let's take a look at our second question. Our second question here, without taking too much of a glance, we know that this question has to do with a quotient. We have a division. So what rule will we use to solve this? We use the quotient rule. Our question says differentiate 3x minus 4 all over 2x plus 1. Let's solve this quickly using our quotient rule. Let's quickly state what our quotient rule states. Our quotient rule states that dy dx, the derivative of our function y with respect to x, is v du dx minus u dv dx all over v squared. All right, so let's go on. Our v here, we said, in our former examples, should be the denominator, while our u should be our numerator. So let's quickly write that down. U is 3x minus 4, while v is 2x plus 1. So next, let's find du dx. if we differentiate our u here with respect to x, we'd have 3. Because the derivative of 4, which is a constant, is what? 0. The derivative of 3x is what? 3. Also, the derivative of v with respect to x would be what? 2. Since the derivative of 1, which is a constant, is 0, the derivative of 2x is 2. So we have our du dx, we have our dv dx, we have our u, and we have our v. We have all that we need to plug into our formula to get our answer. So let's go ahead and do that. dy dx is v 2x plus 1 multiplied by du dx. Our du dx is 3 multiplied by 3 minus u. Our u is what? 3x minus 4. And our dv dx is what? 2. So all of this multiplied by 2. All over v squared. Our v here is what? 2x plus 1 all squared. Let's simplify what we have here. So we have 2x times 3 will give us 6x plus 3 minus 2 times 3x will give us 6x. So our minus 2 times minus 4 is plus 8. All over 2x plus 1 all squared. If we worked out what we have on the board, we would have 6x minus 6x. That would give us 0. And we'll be left with what? 3 and 8. 3 plus 8 would give us 11. All over 2x plus 1 all squared. And that is our final answer. That is our derivative. Let's quickly take a look at our options to see which one we have correctly. A is our correct answer, which is 11 all over 2x plus 1 squared. So here we've come to the end of our class. I guess it was an exciting time for you. I also enjoyed myself, and I definitely look forward to seeing you next time. Bye for now. 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 Bye for now.